Good morning, everyone. We are having our next subject today. The subject is a mixture of actually two different subjects that we will cover today. One would be the unsteady flow, and the second one is UDF, or user defined functions. So let's start with the unsteady flow. Unsteady flow, if you remember the Navier-Stokes equation, in Navier-Stokes equation, we had different terms. And if you remember, one of those terms was the time dependency, meaning the parameters, the velocities, the temperature, and the pressure can change by time. So far, we didn't consider that. So far, whatever we discussed and whatever simulation we performed was time independent or steady state. Even if you remember, in our last session, we discussed turbulence modeling, and one of the characteristics of the turbulence model was to be inherently unsteady, meaning time dependent. But even there, if you recall, we used a method that is called RANS, or Reynolds Average Navier-Stokes equation, which even in that one we used some sort of steady state flow. But today we're gonna deep dive into the subject that, okay, if we want to consider something as a transient flow, what would be the characteristics, how should we approach that, and how the simulation would look like. Before doing that, I should emphasize that going back to our rule of thumb, that make your simulation as simple as possible whenever it is whenever you're not sacrificing something that you need in your simulation. But sometimes in many projects you have to perform transient simulation. But what would be the motivation behind a transient simulation? There could be many different reasons. There could be that, first off, nearly all flows in nature are transient. Okay, so if we want to look at it in terms of the actual physics and the reality of the situation, nearly all flows in nature are transient. But we are considering them as a steady state if we ignore the transient fluctuations, or we are employing some sort of time averaging as we did in turbulence flow. And again, steady state is preferred because of lower computational cost and because of easier post-processing and analysis. But there are many applications that require solution of transient flow. For example, and here we have just named few of them, you have aerodynamics systems like aircrafts, land vehicles, automobiles, bicycles, missiles. These kind of phenomenon the simulation of them would be very useful once you are doing transient simulation. Or rotating machinery like turbines, like compressors, like gas turbines, wind turbines, so on and so forth. These are transient flows. Or multi-phase flows. The multi-phase flows is one of the most important subjects, which we have dedicated one session, actually our next teaching session, to that. So multi-phase flows, especially free surface flows, are inherently transient flows. We have deforming domains like a cylinder in combustion. If you have seen an internal combustion engine, when the explosion happens inside the cylinder, the whole phenomena is transient. Or transient heat transfer, and many other examples that basically you require to perform transient simulation. So let's look at some examples here. There are many reasons. We actually discussed the examples of transient flow, but we have to also discuss that what is the origin or root cause of those transient flows. You either have naturally occurring transients or you have forced transients. So the naturally occurring transients are transient flow due to the growth of instabilities or non-equilibrium initial fluid state. For example, natural convection flows. Remember natural convection or buoyancy flow in our heat transfer? There was no external or outside force. Everything was happening within the system. So it's a natural convection, so it's a naturally occurring transient flow. Or turbulent eddies or fluid waves, they are all some sort of naturally occurring flows. But most of the thing you would see in industry are actually forced transients. The forced transients are basically they have some sort of time-dependent boundary conditions, that those time-dependent boundary conditions basically forces the flow inside your domain to be time-dependent, because we know the flow inside your domain depends on your boundary conditions. And when your boundary conditions are transient, inevitably your flow inside your domain is also transient. Here you can see two examples of it. This is on the left hand side, you have something called KH jet instability or Kelvin Helmholtz jet instability. If any of you guys have taken the multi-phase course of Dr. Ashkrez in mechanical department, you are very familiar with this. This is basically a column of jet of a certain fluid inside another fluid, but which they have a great, or I wouldn't say great, less than 1000 is the ratio of their density. Some sort of instability on the surface of the jet causes the whole jet to disintegrate. So this is, you can see, is a greatly transient, time-dependent flow. On the right-hand side, what we have is basically example of a box falling into the pool of water. This is some sort of forced transient. Why do we call this a forced transient? Simple, because there is an external force, namely here gravity, that causes the whole phenomenon. That's why it's called forced transient. As you can see from the movie, it cannot be, it just can't be simulated and installated, because you won't capture the flow in here. So transient analysis, basically when you are simulating a flow field over a specified time period, you can your solution can have basically, here we have mentioned two scenarios, but your flow can have actually three scenarios. But the third we haven't discussed it here. I will tell you in a minute why we haven't discussed that, because actually we have discussed that previously. So when you are performing a time-dependent simulation, what happens is your solution in time approaches steady state solution. Meaning, for example, take a turbine. When you are simulating a turbine and your parameter, your measurement parameter is the velocity of the air coming out of the turbine. Now assume we are simulating from the whole thing from the start, meaning from the time you push the start button of the turbine to turn it on. Obviously, it is a transient flow because the turbine was at full stop. Once you push the button, it starts rotating and it takes some time to reach its optimum velocity. So until it reaches its optimum velocity, all the parameters, meaning pressure, if you have temperature, on the velocities are changing by time. Now, let's go back to our measurement parameter. Assume we are measuring the velocity at the exit. And if we are measuring the velocity at the exit, when you push the start button and start measuring velocity at the exit, the velocity at the exit would change by time. It will start increasing by time. But after a while, and that while could be 1 minute, 5 minutes, 30 seconds, depending on your turbine, depending on the conditions, the velocity at the exit does not change by time anymore. Why? Because the turbine itself has reached basically the steady state optimum velocity. As a result, your velocity at the exit is not changing by time anymore. That's what we mean by your solution will approach a steady state. So interestingly enough, we had two ways of simulating this turbine. If we do the transient simulation, we will capture from start to the steady state. So we will capture the whole saga. But if we perform in a steady state from the beginning, the part we will be capturing are only the part that is steady state, that nothing is changing. The other scenario for time periodic transient simulation is when your simulation reaches a time periodic solution, meaning whatever parameter you are measuring at your exit, or I mean not exit, anywhere, is always changing by time, so it never reaches a steady state. But what happens is it's changing by time with a specific frequency, like sinusoidal frequency or cosine frequency. That's called time periodic solution or quasi-steady solution. So that's another scenario. The third scenario that we haven't mentioned it in here, but you have to have it in back of your mind, is that it neither reaches steady state nor any time periodic solution. Example, very obvious, turbulent flow. So in turbulent flow, if you include your fluctuations, you are never going to reach to steady state simulation. So your goal may be also to analyze the flow over a time interval. So if we consider all these scenarios, especially the time periodic scenario, it seems that simulation won't have any end because everything is changing by time. For that reason, always have in mind any transient flow, because of our limitations and because it would not be useful for us, we would be simulating it over a specific time period. And the decision about what time period we are talking about comes from the actual case-by-case scenario and from why we are doing the simulation, what we are focusing on, and so on, so forth. In terms of the parameters that we are extracting, I mean in terms of the results that we are extracting from our transient simulation, whatever result that we have discussed so far in terms of contours, vectors, averages, mass fluxes, heat fluxes, so on and so forth, those are all, again, we would need it here, but there are some time dependent specific results that have meanings only that you are doing transient flow. Those are like natural frequencies, RMS values, time average values, so on, so forth. So the workflow for a transient flow simulation is basically as follows. And this is, although we have tried to make it a little bit ANSYS specific, but it's not actually very ANSYS specific, and you can apply the same logic in here to basically any sort of transient simulation. First, you have to enable the transient solver, because you need a separate solver, a separate transient time dependent solver for your simulation. Then, as usual, number two, set up your physical models and boundary conditions as usual. So there is no change here. You will set up your physical models in terms of if you have any reactions, if you have combustions, if you have turbulence, if the viscosity is non-Newtonian, so on and so forth. these parameters have nothing to do with your transient simulation. So you would set those as well as your boundary conditions. Number 3, and this is an extra step, you would set initial conditions for your system. Now we have to a little bit explain this. Initial conditions so far for us in steady state simulation, the initial conditions, if you recall, was your basically initial guess that just before the simulation starts, before the iteration starts, you would provide it to the system as an initial guess, as an initial solution to perform the iteration based on that. But when you are simulating a transient flow, the initial conditions are not anymore your initial guess. Remember, the initial condition in transient flow are your actual physical conditions of the system at time equal to 0, t equal to 0 second. You might say, when is the 0 second? That's your own decision to make. So when do you want to start? It's like a movie. When you're watching a phenomena, when you want to start the camera rolling, that's your time equal to 0. And remember, it is not anymore an initial guess. It's a physical initial condition that you should have very accurately. Once you pass over that step, basically what you do is you will assign solver settings and configure solution monitors. So you will assign any specific numerical solver settings, so on, so forth. Then you would go to your initialization part. So in initialization part, you would provide, you see in here, everything is similar to our steady state simulation. The only difference is you're not providing iterations, number of iterations. You're providing time dependent parameters. You have to provide two things: time step size and number of time steps. So if I want to run a simulation for 10 seconds, so if I want to watch a phenomenon for 10 seconds, right? And if I want to have my time step size as basically 1 second, how many time step would I have? It would be 10 time step. So it would be 10 time steps. So this is will give you an idea how we are going about calculating time step size and number of time steps. Other than that, what you have to decide about is basically the method of time stepping. Is it going to be a fixed time stepping, or it's going to be an adaptive time stepping? So if you put on fixed time stepping, what's going to happen is the software is going to keep your exact time step